tomorrow. Today I just want to get right into this. So we're in this topic. So the overall topic that we're in is 2D particle kinematics. And inside this is a specific topic called circular motion. So we're talking about some specific things that we know about objects that are moving along a circular path. And intuitively, you can think of the velocity and the parallel part of the acceleration and the perpendicular part of the acceleration the same way we did in that two-dimensional accelerations lab. There are a couple of new things. Two just have to do with naming, nomenclature. So for circular motion, so we're not going to do this for other paths that objects can follow, but for circular motion, what we have been calling a parallel, the part of the acceleration that's parallel to the velocity vector, I'm going to denote it as a tan, and I'm going to call it the tangential acceleration. Not just me. I didn't make that up. Everybody calls it that. So tangential acceleration. And the tangential acceleration determines whether the object is speeding up or slowing down, just like it did for any other kind of motion. Also for circular motion, and not for other types of motion, the part of the acceleration that's perpendicular to the velocity, we're going to call, so I'm going to denote it a sen, and this is going to be called the centripetal acceleration. It's always going to act straight toward the center of the circular path, so that's sort of an easy thing about it. And this has to do with turning, and the turning that we're talking about in this case has to do with, keeping the object specifically along that circular path. So to keep the object moving along that circular path. And then there's a third thing that's different for circular motion than other types of motion. And that is, we're going to have ways to calculate the magnitudes of these two parts. So it's not just about visualizing the directions. So we'll actually have formulas for calculating the tangential and the centripetal acceleration. Okay. Generally, talking about general motion along some general path, we didn't have a way to do that. All we could do is visualize the directions. Okay. And these two together, let me just point this out. This is just like the other stuff, but the total acceleration is the sum of these two things. Okay, so if we can calculate the tangential acceleration and the centripetal acceleration, we can add those two together and come up with the total acceleration. Also, this may be something that would occur to you. What's special about circular motion? Because we're not gonna think of every kind of shape and do octagonal motion and square motion and all those kind of things. Why do we care about circular motion? There's sort of one pretty simple answer for that. Yeah.
There's a constant acceleration. Like there's a constant.
There is, okay, so there is one thing about, there's a certain like simplicity to it having to do with this stuff, and so that makes it possible to calculate it. I think that's a reasonable answer. But the answer that I think you should keep in mind is that it's really important for engineering applications because anytime you have rigid body motion, any rigid body, think about like my forearm or something, choose some point on my forearm, it's moving in a circular path around this hinge. And if you make a machine out of all these different parts and all of these rigid bodies are moving together, you can think of that as a sequence of circular motions of points around other points. And so if you calculate the motion of this thing around its joint and that joint around the joint it's attached to and so on, you can do a lot of complicated machinery calculations using circular motion. Okay, so there's a connection between circular motion and rigid body motion that makes this really important. Okay. All right, so let's first, before I start getting into the calculations, let's think about an object that's moving in a circular path like this. So let's say the object is moving counterclockwise along this circular path. While slowing down. So what's the direction of the velocity vector? What's the direction of the tangential acceleration? What's the direction of the centripetal acceleration? And then before we do any calculations, so without calculations, what do we know about the direction of the total acceleration vector? So about the direction of A. Okay. Well, this is the center of the circular path. The object is moving counterclockwise. So I drew the circular path is drawn in here. Counterclockwise is this way. So the velocity vector is tangent to the path, like that. Okay, this is just the stuff that we did in lab last week, except now we have new names for the parallel and perpendicular parts of the acceleration. It's slowing down. So is the tangential acceleration the same direction as velocity or opposite? Opposite. So there's the tangential acceleration. The centripetal acceleration is, there's always a simple answer for that. In circular motion, it just points right toward the center. And notice those still have to be perpendicular to each other. The center, going toward the center, is always perpendicular to the tangent. And then last, what do we know about the direction of the total acceleration vector? Well, we're going to be able to calculate the magnitudes of those. That's something special that we're going to have about circular motion. But before we do those calculations, we can say that the total acceleration is somewhere in between those two directions. Okay. Any questions about that? All right, so now we need to learn how to calculate the magnitudes So how to calculate the magnitudes of these vectors, because we already know the directions. And to do that, I'm going to introduce these angular quantities that are analogous to some things that we're already aware of. So I need to introduce some rotational or angular analogs of translational quantities we already know. I'm going to just set up this little table with two different columns. The first one is the stuff that you're familiar with, translational. And then over here is the rotational or angular. Those are synonymous. So the first pair of analogous quantities are the position. and that has units of length. Oh, and we, call that P vector. And the analogous angular quantity to this is the angular position. We'll call that theta. And that has units of radians, but it's also pretty rad once you get used to it. That was stupid.
She was pretty rad.
Okay, the second one is, and so why I'm making these connections between these two sets of things, because a lot of the stuff that we're introducing, these angular quantities, you can kind of store in the same part of your brain that you store these translational ones. A lot of these relationships are going to be similar, we're going to see. So the second one is the velocity. V, and the units are length per time. And the relationship between velocity and position is that the velocity vector as a function of time is the time derivative of the position vector as a function of time. You can think of that as the definition of the velocity. The analogous angular quantity is the angular velocity. This is going to be denoted with the Greek letter omega, lowercase omega. And this has units of radians over time. And I said a lot of these, the relationships between these angular things are going to be similar to the relationships with the translational things. So if you had to guess, no one likes to guess without knowledge, but you had to, or they're going to take your dog. What would you guess is the definition of the angular velocity as a function of time? Yep, exactly. So this is the time derivative of the angular position. Okay. And then the third one, the last one, the translational quantity is the acceleration vector. So that's A, and that has units of length over time squared. And the analogous angular quantity is the angular acceleration. We'll denote that with the Greek letter alpha. Goldfish looking thing. So it's like the Greek A. And the units of this will be radians per time squared. The definition of the translational acceleration as a function of time is the time derivative of the velocity as a function of time. So what would you guess the angular acceleration as a function of time is?
Maybe
That's correct. You get to keep your dog. Okay, so there's a lot of similarities there. And so now I just have to go through and define these. So the angular position first. Theta. So if an object is moving around a circular path, and here's the center, and this is some reference line. Usually that reference line is the, like the positive x-axis, but it doesn't have to be. You just have to choose a reference line. And say that this is the object at some given instant, some desired instant. Then the angular position is the counterclockwise angle from that reference line. So this is the desired point on the circular path. Okay, so we're going to be, this is in radians, I said, right? So we're going to be dealing with these angles in radians. But you're not going to have to, for this, change your calculator from degrees to radians, because for the most part, we're not going to use trig functions with these. Okay. But we'll see why we need to do this in radians as we go on. If theta is positive, that means that we've gone counterclockwise from the reference line. And if it's negative, that means clockwise. So in the picture I drew here, this theta is positive. Like I said, the units are radians. And remember, radians has this property that it's not really a unit. Like when I write in radians, it's just to let you know that it's representing an angle. It's kind of like an intuitive thing. But really, representing angles in radians is just representing angles as a pure number. Okay, so what we're going to see is, like, if you multiply something with units of radians to something with units of meters, you end up with something with units of meters. Those radians are not really a unit. Okay. So you can also think of this as unitless. And now angular velocity. We're going to represent with this Greek letter omega. And omega as a function of time. You can think of this as the definition. This is always true. is equal to the time derivative of theta if omega is positive, that means that the object is moving in a counterclockwise direction around the circular path. And if omega is negative, it means it's moving in a clockwise direction. So object moving clockwise around the circle. And so one thing I want you to notice is that means if you know the sign of omega, that's enough for you to know the direction of the velocity vector. Okay, we haven't talked about how to calculate the magnitude yet, but if you think of this object, so if omega is positive, then at that instant the object is moving counterclockwise around the circle. Okay, and if it's moving counterclockwise around the circle at this instant, then the velocity vector is tangent to the circle this way. Okay, and if omega is negative, that means at this instant it's moving clockwise, and so the velocity vector is that way. Okay, so there's a connection between the sign of the angular velocity and the direction of the velocity. Okay. And the units, I said this above, but the units are radians divided by time, or in other words, you can think of that as just 1 over time, since radians aren't really a unit. And now the angular acceleration. This is alpha. The definition of the angular acceleration as a function of time is the time derivative of the angular velocity as a function of time. So you can think of that as the definition. If the object is speeding up, sorry, let me reword this. So if omega and alpha have the same sign, what would you guess is happening with the object's motion? Yep. So in that case, the object is speeding up. And if omega and alpha have opposite signs, then the object is slowing down. And now this works similarly to the way the angular velocity works. So I want you to notice this. The sign of the angular acceleration is enough to specify the direction of the tangential acceleration. So you can think of if alpha is positive, that's a counterclockwise angular acceleration, and if alpha is negative, that's a clockwise. So let's look back at this picture again and say that you have a, let's say that you have a positive alpha, positive angular acceleration. Okay, so the direction of the angular acceleration at that instant is counterclockwise. Well then, which direction would the tangential acceleration be? You know, the parallel part of the acceleration. Would it be this way or that way? Like up or down? Up and to the left. Okay. Any questions about that? If the angular acceleration is negative, that means at that instant the angular acceleration is clockwise, and that means that the tangential acceleration is tangent to the path that way. Yep.
So is this really more like the 1D kinematics than it is like the 2D kinematics, because they're really two directions?
Yeah, that's right. So yes, in this case, the axis of rotation, so you can, you know, the axis that this rotates around is always parallel to the z-axis, you know, and so you can represent a two-dimensional circular motion direction just with a positive or negative sign. Okay, you don't. So we're not going to have to use vectors. Although it turns out that when you do use these angular quantities in 3D, the axis of rotation can move anywhere, and so when you go on to 3 dimensions, which we're not going to do in this class, omega and alpha are actually 3-dimensional vectors. But for now, we're going to treat them like they're scalars. Okay, and just the sign gives us the direction. Okay, so the first thing, let's see. No, not the first thing, the only thing. Okay, so now we're finally going to use these angular quantities as a way to calculate the magnitudes of translational quantities. So this is kind of the big step for our calculations. These are the relationships between angular quantities and the magnitudes of translational quantities. So remember, we already can, like intuitively, by just understanding what the directions mean, we already can figure out the directions of the translational quantities from the signs of the angular quantities. So all we need then is the magnitudes, and this is how we get the magnitudes. So the first one is, I'm going to call this the 0 one. We're not really going to use this. That's why it's in parentheses. But the displacement around the circle you can think of that as the arc length. Is the radius of the circle times the change in the angular position. You've used that before in geometry. But here are the three that we're going to use. So first, the magnitude of the velocity. And you can denote it as the magnitude of the velocity vector like this, or a lot of times people show it as a capital V. And what's another name for the magnitude of velocity? Speed, yep. And so V, capital V, or the magnitude of the velocity, those mean the same thing. And it's equal to the radius of the circle times the absolute value of the angular velocity. What are the units that you get from multiplying the radius of the circle times the angular velocity? Well, it should be, since we're calculating a magnitude of a velocity, we know it should be length over time, right? And it works out because the radius of the circle has units of meters or length, okay? The angular velocity has units of 1 over time, radians over time, which is 1 over time. And so it comes out the way you would expect. Okay. Okay, so this is always positive, and that means that this doesn't give you the magnitude. It does give you the magnitude. It doesn't give you the direction. The direction you have to get from the sign, from that intuitive understanding. The second one is the magnitude of the centripetal acceleration. So remember, this is the part of the acceleration that's perpendicular to the velocity. This is the one that makes the thing move in a circle, deals with the turning that keeps it moving in a circle. So we're talking about the magnitude of the centripetal acceleration. And that's equal to omega squared times r. I didn't need to use the absolute value because of the square. And if you also use, if you substitute the first one in here, that's also equal to v squared over r. And what are the units for omega squared r? what are the SI units for omega squared r? Meters per second squared, and really you don't have to think through the units of omega squared r to come up with that answer. You just know that it's giving you an acceleration, so it has to work out that way. Okay. And that doesn't give us direction, only magnitude. So what's the direction of the centripetal acceleration? It's toward the center of the circle always. So that's a pretty easy one. Okay. Centripetal means toward the center. Okay. And then the last one. So the third and last magnitude, what's it going to be? What's missing so far? The tangential acceleration, yep. So the magnitude of the tangential acceleration that's a tangential and that is equal to r times the absolute value of alpha. Okay, so any questions? Let me do a quick example problem. Okay, so let's say that you have this circular motion and the radius of this circle is 0.1 meters. And this is the point that we care about. That's where the object is at the point we care about. And let's say that, so at the point A, omega is equal to -20 radians per second. Alpha is equal to +10 radians per second squared. And we want to know what are the velocity vector and the acceleration vector at that point. Yep. Yeah, so let's think about, so the way we're going to go through this is think about the directions first like that, and then we'll do the calculations and include those. Let me just move this down here. Okay, so yeah, let's think about the directions. The angular velocity is -20 radians per second. So is it moving clockwise or counterclockwise? Okay, so the angular velocity is this way, and that means that the velocity vector is this way. The angular acceleration is positive, so is that clockwise or counterclockwise? Yeah, positive is counterclockwise. And so what's the direction of the tangential acceleration? There are only two possible, it has to be parallel to V. So is it up or down? Those are the only two options. And since alpha is counterclockwise, this has to be down. And then centripetal acceleration is always toward the center. So we know all those directions. And that means that once we calculate the magnitudes, we can express these as vector components. Okay. The magnitude of the velocity vector is the radius times the absolute value of negative 20. Let's see. So that's 2.0 meters per second. And so combine that with the direction that we figured out. I didn't draw a coordinate system yet, but let's just use the one we're used to. We know that v is in the positive y direction. So that means this has to be 0, positive 2. Yep. This is radians per second, but the radius is meters. And so when you multiply them together, you get, meters radians per second, and the radians are not really a unit, so meters per second for the velocity. You could write it as radian meters, but I'll take all the points away. Not really. Okay, now what about the tangential acceleration? So the magnitude of the tangential acceleration is r times the angular times the magnitude of the angular acceleration. So that's 0.1 times the absolute value of 10. And so that's 1.0 meters per second squared. That's in the negative y direction. So the tangential acceleration is 0, negative 1. And then the last one is the centripetal acceleration. The magnitude of that is omega squared r, or we could use v squared over r in this case since we already calculated v. But that is 20 squared times 0.1. So that's 40 meters per second squared. That's in the positive x direction. We figured that out earlier. I just didn't label it. And so the centripetal acceleration is positive 40, 0 meters per second squared. And so now the total acceleration is the tangential plus the centripetal vector. And if you add those two together, you get 40, negative 1 meters per second squared. Any questions about that? Okay, that's all. See you tomorrow.